Welcome back. Let's talk about another counting technique, and this one applies to counting sequences. Sometimes what you're counting is best represented as a sequence of objects, or instead as a sequence of independent choices. We make a first choice, and then we make a second choice. The strategy in this situation is that we want to determine the number of choices at each step and then multiply them together. For example, you have in your closet 15 tops, 10 bottoms, and 5 pairs of shoes. How many different outfits can you make from these clothes? The answer is there are 15 tops, 10 bottoms, 5 shoes. If we multiply those numbers together, we get 750 outfits. What is it about this situation that makes it that we can multiply these numbers? The key is that no matter which top you chose in the first step, there are always the same number of choices for the bottom to go along with it. And no matter which top and bottom pair you chose, there were the same number of choices for the shoes. So this is the monologue that you need to have going on in your head. At each step of the process, the number of choices was independent of the previous choices that were made. This is the thing you need to verify in order to multiply the numbers together. We can also understand this as a situation involving sets. We can think of T as the set of tops you can choose from. We can think of B as the set of bottoms you can choose from. And we can think of S as the set of shoes you can choose from. Then, what we're trying to count is the set of outfits. And mathematically, we can write that as a Cartesian product. The set of outfits is the Cartesian product of T with B and S, and that's because every outfit is a triple, a choice of top, bottom, and shoes. This principle is called the multiplication principle. If A and B are sets, then the cardinality of the Cartesian product of A and B is the cardinality of A times the cardinality of B. And in general, if we have many sets, then the size of the Cartesian product is the product of the sizes of each of the individual sets. So here's how you go about applying the multiplication principle. Your goal is to count a collection of objects, and you recognize that you can understand your objects either as a sequence itself or a sequence of choices. Then you verify that the number of choices at each step is independent of the previous choices. Then you count the number of choices at each step individually, and you multiply those numbers together. Let's see a few examples. Our first example is an example that will come up a lot, and that's the idea of words in an alphabet. Let's define an alphabet A to be a set of characters, maybe something like the set A, B, C. A word on this alphabet is a sequence of characters. So maybe we have AAA, maybe we have BABC, maybe we have CC. Or maybe we have the empty word with no characters. The length of a word is the number of characters. So the length of AAA is 3, the length of BABC is 4, the length of CC is 2, and the length of the empty word is 0. You can see that these words are not words like we're used to, where they mean something. Instead, a word is simply a sequence of characters, whether or not it means anything in English. Another terminology for words in an alphabet are lists with repetition. We think of this word AAA as an ordered list, and the entries of the list are allowed to repeat. A natural question to ask is how many words there are of length K on a particular alphabet, such as ABC. Every word is a sequence. A particular word is a sequence of characters, W1, W2, up to WK, where each WI is a character from the alphabet. If we look at the first letter, W1, there are 3 choices for it. It could be A, B, or C. Now, no matter what letter is chosen for the first letter, the second letter could be A, B, or C. And as we continue down the word, at every step of the way, no matter what letters have been chosen, there are always 3 choices for the next letter. And this is the key. At every step of the way, the choices at the next step are independent from the choices that have come before. And so we can apply the multiplication principle. The set of words is equal to the Cartesian product of k copies of the alphabet. And that means that the number of words is equal to the size of the alphabet multiplied with itself k times. That's a general statement, and for a particular alphabet, A, B, C, there are 3 choices for each, and so the total number of words is 3 to the k. We've seen words on an alphabet before, binary numbers, like 010, 111, or 00100. In that case, the alphabet is the set 01. The number of binary words of length k is going to be 2 to the k. That's really nice.